Hi, thank you for joining us for the Consulting Specifying Engineer webcast, Electrical Distribution Systems, sponsored by ABB, Cyber Sciences, and Starline, a brand of Legrand. I'm your moderator, Amara Rozgis, with Consulting Specifying Engineer and CFE Media and Technology, and I'll be with you for this hour-long education session. Let's learn about this platform. If you're having trouble with your slides or with the sound, please refresh your internet browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your own device. If you're having technical problems, click on the question mark at the top right corner of your screen to do some system checks before contacting an online technician. If you do need help, please type a message into the Ask a Question box and we'll respond in the Answered Questions box. To download this presentation, use the Event Resources on the left side of your screen. Type questions for the presenters in the Ask a Question box on the left side of your screen. You may ask questions at any time during the presentation. The Q&A portion will start in about 45 minutes. If you're interested in receiving one AIA CES-approved learning unit for this event, you need to pass a 10-question exam. To take the Learning Unit exam and to download your AIA CES certificate, use the Learning Unit exam tab at the top of your screen. The quiz will open in a new browser window, so I recommend you open that tab right now because it will break when the webcast signs off. In keeping with the AIA American Institute of Architects Continuing Education System Policy, please take a moment to read the quality assurance slide. Here are the learning objectives. We'll talk about these in today's presentation. Please note that any red, underlined text you see is a hyperlink in the PDF where you can get more information. Let's now hear from our session's sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for mixed internet speeds. Please stay tuned after the videos for today's presentation.
For critical facilities, always-on reliable power is essential. Power outages can be costly, as well as damage your reputation, and can lead to increased liabilities and non-compliance issues. No matter how well designed, no system can operate indefinitely without failure. When something goes wrong, you need answers, and fast. At Cyber Sciences, we provide precision timing for accurate event recording, helping minimize cost and time of recovery after a power event. Precision timing is essential for event reconstruction and post-event analysis. In complex electrical networks, state changes can occur quickly. Thus, system-wide clock synchronization is needed for meaningful data analysis. With products made in the USA and available worldwide, Cyber Sciences provides accurate event recording down to 1 millisecond. Cyber Sciences, the world leader in critical power loss event recording.
Starline Track Busway T5 series ranges from 250 up to 1250 amps. The busway runs overhead and provides power to server racks in mission-critical environments, and to machines and equipment used in assembly and manufacturing. With Track Busway, you can connect power at the point of use and easily rearrange for future changes and expansion. Plug-in units can be engineered to order and are interchangeable on any T5 system. Our patented U-shaped copper bus bars ensure the most reliable connection on the market. For more information on the Starline Track Busway T5 series, please visit starlinepower.com.
We know that safety is always a top priority. Are you keeping up with the innovations helping to make safer power distribution possible? From the largest piece of arc-resistant switchgear to the smallest arc fault and ground fault sensing circuit breaker, ABB is designing ways to help lower the risk of harm to both people and equipment. A forgotten tool inside the enclosure is a common cause of arc flash. Reduce the risk of a tool coming in contact with the bus stack or breaker connections with ABB's IP20 certified bus stack. Help enhance operator safety with groundbreaking T-Max XT circuit breakers. Remote metering and monitoring allow users to access information anytime, anywhere. With support for over 10 communication protocols, you'll always be connected to what's happening in your power distribution system. Optional Bluetooth connectivity allows personnel to set parameters and check measurements directly from their smartphone, all from an arc-free zone. Accessories like reduced energy let-through modules help to further enhance operator safety. And surge protection devices and advanced voltage and frequency protections can help prevent power quality issues from damaging sensitive equipment as well. Work safer and protect your assets with innovative design.
All right, well, we have lined up two extraordinary presenters today. John Yoon is the lead electrical engineer at McGuire Engineers in Chicago. His expertise in the field of electrical engineering is the product of more than 20 years of experience in the design of electrical distribution systems, emergency systems, and lighting design. John is a member of the Consulting Specifying Engineer Editorial Advisory Board. Jeff Thomas is Vice President and Business Group Director with Lockwood, Andrews, and Newnham, based in Houston. He's an electrical engineering expert with 28 years of experience as a project manager, energy manager, auditor, and certified healthcare instructor. All right, gentlemen. John, you're up first. Let's get started.
Thanks, Amara. For this webinar, we're starting out with an excerpt directly from Article 90, the Introduction to National Electrical Code. The stated purpose of the code is to safeguard people and property from the hazards associated with the use of electricity. So when we design electrical distribution systems, the typical focus is on ensuring that the equipment and wiring methods that we specify have appropriate capacity and configuration to reliably serve whatever loads may be connected to that system. However, what we often lose sight of is the fact that there are inherent hazards associated with the use of electricity. Ultimately, when we design electrical distribution systems, we need to be able to interrupt the unintentional flow of electrical current before it can cause harm to people or damage equipment. For the beginning of this webinar, let's start with the basics. How do you characterize what that unintentional current is? So when we talk about unintentional or objectionable electrical current, we're typically talking about overloads and faults. These two are distinctly different things. Let's first take a look at what the concept of an overload is. The NEC definition is shown on this slide. You can read it yourself. But based on this definition, a fault such as a short circuit or a ground fault isn't an overload. If you read into this, the key takeaway should be that the current is flowing through the circuit that you designed through that normally expected path, whether it be through a transformer, a motor, a feeder, whatever load or wiring method you may have connected to that circuit. However, the magnitude of that current is more than what you want. It could be sustained locked order current associated with a seized motor, too many appliances plugged into a circuit. It could be any number of things. Faults or short circuits, on the other hand, are where current flows through a path other than the intended load or circuit. Oddly enough, the NEC doesn't formally define all types of general faults or short circuits. Only ground faults are defined within Article 100. The ground fault definition is indicated on this particular slide that you can read yourself. Give you a second to take a look at it, and let's move on to the next one. So, that brings us to the question. We have two different types of conditions, overloads and faults. How do you safely interrupt this abnormal flow of electricity? With an overcurrent protection device. Well, let's continue with another excerpt from the Article 100 definitions, the definition for an overcurrent protection device that's on this slide. So what qualifies as an overcurrent protection device? This could be a fuse, it could be a multi-case circuit breaker, it could be a protective relay, whatever. However, what isn't noted here very conspicuously is a timing requirement, how quickly that device needs to operate. While the code in some cases makes mention of how quickly a device needs to operate under very specific conditions, it generally is more a function of the UL standard associated with that particular device type. Moving on to the next one, let's start with fuses. Fuses have been around for an extremely long time. The picture that you see in this particular slide is part of a 5,000 amp 208-volt live front switchboard from the 1940s. You can clearly identify the individual fuses, fuse clips that they're seated in, everything else. Although it seems wildly obsolete and unsafe, this switchboard is actually still in operation. So even though fuses have been around for what seems like forever, there's no formal definition within the NEC for what a fuse is. As such, we have to rely on definitions from another source. There are two applicable standards for fuses, UL 248 and NEMA FU1. Let's start with the NEMA definition. A fuse is a protective circuit that opens a circuit during a specified overcurrent condition by means of a current responsive element. That element is the fusible portion of the fuse that melts during an overcurrent condition to clear the circuit. Basically, that's a sacrificial conductor that melts, maybe even vaporizes, depending on the magnitude of your current. When exposed to an overcurrent condition, it opens the circuit and prevents damage to those downstream devices. So let's take a closer look at how a fuse works. Under normal operating conditions, that element has reasonably low resistance, so it is functionally no different from any other conductor. However, in an abnormal operating condition, we depend on a sacrificial element. We either have to melt or vaporize that element to open and interrupt the circuit. If that happens in free air, the act of melting an element and releasing that energy, that in of itself could be potentially dangerous. As such, we have to somehow contain or dissipate that energy. So that element is installed within that cartridge body that you see in the picture and is usually surrounded by sand to contain and dissipate that released energy to quench any arc that's formed. Traditional single element fuses are a compromise, either protecting against short circuit or protecting against an overload condition. You can design that single element to melt very quickly and have it be very fast acting, or you can sacrifice the speed and have it be a time delay type fuse. But this is a pretty significant trade-off and is unacceptable when you're trying to protect loads of very high inrush currents like motors and transformers. To address this issue, the fuse industry came up with the concept of a dual element fuse. Now, that's exactly what it sounds like. You have two separate elements connected in series together, one optimized for the low magnitude overcurrent condition and the other for the high magnitude fault condition. The vast majority of fuses that you encounter in low voltage power distribution systems will be of this dual element type. Moving on. So let's move on to how the element in the fuse reacts to various magnitudes of overcurrent. Based on what we've seen so far, you should be getting the impression that these overcurrent protection devices will react very differently depending on how much current they see, whether it's a minor overload or a bolted fault on the other side of the spectrum. To be able to compare two different types of overcurrent protection devices, use something that's called a time current curve. All manufacturers have these and are of a similar format, so you can make easier comparisons between two different devices. If you look closely at this graph, you notice that the scales aren't linear. This is a log-log graph. So our per unit values go from 0.1 to 1 to 10 to 100 and so forth and so on. And these time current curves, time in seconds is always on the vertical y-axis and current in amps is on the horizontal x-axis. In this particular time current curve, this is for a generic 100 amp fuse. The red band that you see here represents the minimum and maximum melt times for the elements in that fuse. Everything to the left of that curve is normal operating conditions and the fuse will not open. Once you hit the red band or go to the right of it, the fuse will open the circuit. So, So you can see that that thin red band, it has some weight to it. This is due to manufacturing tolerances. So the fuse is guaranteed to open somewhere within that band, not necessarily an exact number, but somewhere in that band. You can also see if you follow the graph up the time scale towards the top at the 200 second mark, if you cross-reference that with current, you can see that the fuse actually holds substantially more current than 100 amps for that period of time. Before we leave this slide, let's take a look at the bottom of this curve. And you can see where we have a very high magnitude of current, how that fuse reacts in a fault condition. This will become more important when we're comparing these to circuit breakers. Let's move on to circuit breakers now. Again, we have another definition from the NEC that you can read. Based on this definition, a circuit breaker can be open and closed against all magnitudes of current up to its short circuit rating, basically acting as a switching device. The UL standard applies to most common types of circuit breakers, molded case circuit breakers, UL 489. Again, the NEC doesn't necessarily dictate how quickly a device must interrupt that abnormal flow of current. That requirement is defined by that UL standard. One important point is that when UL test circuit breakers, they are tested for their rated ampacity and free air. When they're installed within an enclosure, unless they are specifically rated for 100% duty, they must be derated to 80% when subjected to continuous current. Continuous currents are defined in the NEC for any load that is sustained for 3 hours or greater. Okay, let's move on to the next slide and talk a bit more about this. Again, we have two distinct conditions that we're trying to protect against, overloads and faults. These two conditions are characterized by the magnitude of unintentional current. There's a big difference between these two. We saw how a dual element fuse addresses these two conditions. But the question is, how does a circuit breaker address those same two conditions? A breaker does this by two distinct mechanisms, a thermal function and a magnetic function. The thermal function is accomplished with a bimetal strip. The bimetal strip is two interconnected pieces of metal, and these two pieces of metal have slightly different coefficients of thermal expansion. They will shrink and expand at different rates when heated, like resistive heating when you have current flowing through them. This causes the strip to bend and release a latch to trip the circuit breaker open. The magnetic portion of the breaker works on the principle of electromagnetic fields created by the flow of current, the right-hand rule. The magnitude of the field is proportionate to the magnitude of current. Through design of the breaker, you can create a magnetic field that will force a switching armature open. More current means greater magnetic field, which will open the contacts much faster. When subjected to full fault current, the typical circuit breaker will open in a half to one cycle. When we look at time current curves a bit later, this will become a little bit more apparent. So this is a picture of what we just described. We have the bimetal element that handles the overload side of it. We have a magnetic element that handles that short circuit part of the equation. And like they say, a picture is worth 1,000 words. Hopefully this makes things a little bit clearer. And when you think about it, it's almost like a mousetrap. Once you trip that latch, the spring will draw the circuit breaker open. And either the magnetic element or the bimetal element can trip that latch. So let's move on to how a thermomagnetic circuit breaker responds to various magnitudes of overcurrent. Here's a time current curve for a generic molded case circuit breaker. Again, we have a log graph of this how this device responds to various level of current. The blue band that you see represents the minimum and maximum maximum trip thresholds for this breaker. Everything to the left of the curve is normal operating conditions, and the breaker will not open. And again, similar to a fuse, everything on the right side of it will open and interrupt the circuit. However, you can see that blue band is much wider than the fuse we were looking at before. The breaker is guaranteed to open somewhere within that band, but there's a lot more uncertainty regarding exactly where. Finally, at the base of the time current curve, we see that instead of a smooth curve at the bottom, we have a weird dog leg at extremely high current. Basically, a level of current that you would typically expect with something like a bolted fault. You can see that responds extremely fast. Again, half to one full cycle, but that blue area extends out to the right. Now we have a certain level of uncertainty. All UL 489 breakers have this characteristic dog leg in the instantaneous region, which can become a selective coordination issue. With some types of solid state trip units for circuit breakers, you can adjust the pickup setting, but if the breaker is UL listed under 489, it cannot be defeated, only adjusted. Again, the equipment downstream of this that you're trying to protect with these breakers is typically only rated for 3 full cycles of fault current. Moving on. Now, with a fixed mechanism like that for a generic fuse or circuit breaker, we have pretty well-defined characteristics regarding how each device will respond to magnitudes of overcurrent. But in an electrical distribution system, we have multiple devices in series, each with its own characteristic time current curve. When we design electrical distribution systems, we're trying to isolate an abnormal condition to the smallest portion of the distribution system. We want the device closest to the fault or overload to operate first, to have what we call selective coordination. With multiple devices in series, there's bound to be some overlap and will lend some uncertainty regarding what device will trip first. Given the various types of scenarios that you may encounter, being able to tweak or make minor adjustments to how that individual breaker reacts to certain conditions can make all the difference in the world. To this end, some breakers can be provided with an electronic trip unit. With electronic trip units, we're replacing a purely mechanical tripping mechanism, like in that picture, with an intelligent module that senses the true RMS current flowing through it with current transformers. Depending on the breaker, you can shape or tweak multiple portions of that time current curve. These trip units sense overcurrent conditions very quickly, but you're limited by the fact that it still has to operate a mechanism to open the circuit. See, we're a little shorter on time. Let's keep on moving a little bit faster. So we talked about both fuses and circuit breakers. Let's directly compare the operating characteristics of the two. Of course, there's a credible variety of fuses and circuit breakers, each with its own specific time current curves. However, to illustrate a point, let's look at that generic fuse and circuit breaker time current curves. This picture is a direct overlay of both of these. The fuse is red, the circuit breaker is blue. When they are overlaid, the difference is quite pronounced. You can see that the characteristic transition between the magnetic function and the thermal function in the blue band is at about half a second or 30 cycles. We can also see that in this particular case, the circuit breaker reacts considerably faster in the overload region of the graph at the top. However, when we take a look further down in the short time region of the graph where the magnetic function of the breaker operates, there's pretty high uncertainty regarding where the circuit breaker will clear default in comparison to a fuse. If we go down to the bottom of the graph again, see that dog leg that's characteristic of a thermomagnetic breaker. That top of that dog leg is at 1 cycle. 0.0167 seconds. The circuit breaker can trip anywhere within that shaded blue region, whereas with the red band representing the average melt time for the fuse is really well defined in this region. So down there, I can't tell you if the fuse or circuit breaker is going to catch first. All right, there are some people that prefer fuses. There are people that prefer circuit breakers. So everyone has their own personal preferences. However, we're not here to say that fuses or circuit breakers are better and worse. Rather, based on your particular application, you should understand relative advantages and disadvantages of each, and then make a determination what makes the most sense for your budget protection. Now, we have a bunch of items here. I suggest that you download the slides and you can actually review these at your own pace, because trying to cover them is going to take a lot of time. But before we leave this, let's just say that most fuses are current limiting, but there is a concept called threshold current ratio. Basically, if the fault current is equal or greater than the threshold current, the fuse is current limiting, and this ratio can be anywhere from 30 to 65 times the rated ampacity of fuse. So this is great when you have a high level of available fault current, but for low magnitudes of fault current, like an arc fault event, they may not be particularly effective at limiting that fault current. So we also have pros and cons for circuit breakers. Again, we're not going to read through all of these, but you can see that one of the primary advantages that we have is we can have solid state trip units that we can perform additional functions that the fuse can. We can shape the shape of our time current curve so it reacts differently. All right, let's hand it back now to Jeff, and hopefully can make up a little bit of time. Sorry, Jeff.
Thanks, John. I appreciate it. So you heard John mention codes and you heard John mention standards. So let's talk about the differences. Codes typically are enforced by governmental agencies and govern the installation of systems to ensure safety. Everything you heard John talk about with the NEC, it talked about safe operation, protection of this, protection of that. That's what codes are for. Standards are typically driven by industry and govern how components and assemblies perform. You heard him talk about UL 489. You heard him talk about other standards that govern how the breakers operate. And if a breaker is going to operate in a particular way, it must do this and do that to meet the standard. Those are two very different things, but they both play a part in our design work. Some of the codes that we play with all the time are pretty much all under the umbrella of the National Fire Protection Association. National Electric Code just happens to be Chapter 70 of the NFPA. Then we've got 70E for electrical safety. I mentioned 99 for Healthcare Facilities Code. Anybody who does electrical work in healthcare facilities will be very familiar with Chapter 6 of 99. There's also NFPA 54, the Fuel Gas Code. Anybody want to run a generator? We're going to want to know about fuel gas. And then the one outlier that we will typically deal with if we're doing buildings is the International Energy Conservation Code. Interestingly enough, it's a code when it's really a collection of standards that talk about how a building should operate in terms of conserving energy. But these are all highlighted here and hyperlinked that you can click on and read at your leisure. Standards organizations also come into play, and some of these you should be familiar with. Underwriters laboratories we talked about. They're kind of the one gray area where they sort of venture into the safety realm more than just the operational realm. A lot of components must be UL listed in order to be approved in installations. Then there's NEMA, which we're all familiar with, Canadian standards, ANSI, and ASTM. Again, click on the hyperlinks, get familiar with all these codes as you need to. John mentioned UL 489 for breakers. There are also some key standards for switchgear. 1558 governs metal enclosed low voltage power circuit breakers, and 891 talks about standards for switchboards. And these will all be taken into consideration by the design professionals as they're designing the installation. All of the codes and standards help with reliability. And let's touch on reliability and the bigger picture, resiliency and redundancy. Everything we do in electrical systems, we want them to be reliable. And nowadays, we want them to be resilient. And in some cases, we'll do that with redundancy. Generally, our utilities are pretty reliable, okay? But as we know, there are always mitigating circumstances, all right? Storms, floods, freezing events for those of us down south just really play havoc with utility systems. If you read all the tariffs from your utility companies, which I'm not going to read for you, every one of these things basically says it's the customer's responsibility for reliability. If you want your equipment to run 100% of the time, that's on you, not them. So what you have to figure out is how critical is your function? Are you a hospital? Are you a commercial office? Or are you something in between? Only you can determine how critical you are. Some reliability data from utilities that will help you in your decision making. You know, a utility typically says we go down 3 hours per year. We have 23 voltage sags below 70%. 70% is where typically equipment will drop offline. Can you tolerate those in your installation? How much insurance do you need? And I use the word insurance because basically that's what this is. We are ensuring that our facility will remain up and running during a utility outage or event. A couple of strategies we'll touch on briefly. The two extremes, I call this the hardening of the facility, the robust strategy. This is if you have an infinite budget. We make the facility flood-proof. We make it storm-proof. We've got multiple backups and backups of backups. We've stockpiled fuel and supplies, and we've got shelter-in-place accommodations for all of our staff. Option one, very, very expensive, but in some cases, maybe you have to do it. If you're a critical healthcare facility, level 5 trauma center, you may have to go to these extremes. On the other end, what if we just abandoned the facility and ran away until the event was over and then came back? It's a perfectly valid strategy. Those of us in Houston during the February Snowmageddon event, that's what a lot of us did. We shut off the water to our houses and we drained the pipes and we left. And then when the weather warmed back up, we came back. Quick restart is key to that. And our electrical systems can be designed to support that as well. We've got some strategies as we look at our electrical systems design. multiple utility feeds, generators, redundant switchgear, uninterruptible power supplies. If you're running a data center, much equipment these days comes with dual supplies. And then you can even use alternative energy sources, solar, wind, fuel cells, cogeneration, other form of backup generators. All of these can be factored into a resilient and robust facility. So let's talk about the components of a distribution system that'll help us create these facilities to operate the way we want them to. So in this slide, you can see this is kind of a high-level tree of where we do our electrical distribution system. So we start with service entrance switchgear, something called the point of common coupling, or the PCC. This is where we connect to the utility. So everything to the left, which is not shown in this slide, would be the responsibility of the utility. Everything to the right is ours. So this shows sort of a medium to large 480 volt primary service installation. So we come in from our switchgear, there's some sort of metering because the utility is not going to do it for free. We've got a main switchboard, which would then break off into a variety of distribution boards. Perhaps we've got a high voltage distribution board at the top there that feeds motors and large demand loads. Maybe we have large electric heat systems, as well as pumps and fans and so on and so forth. In the old days, actually in the not too recent old days, we would always have a high voltage lighting board because most of our lighting circuits were 277 volts, and which would then be its own separate panel and be controlled accordingly. Then we would run into a high voltage to low voltage transformer, and this would knock us down and get us into the convenience outlet realm. The distribution board would fed from that transformer and run all of our 120 volt standard receptacle loads. All right, this is pretty typical for a larger installation. What about smaller installations? Suppose we're doing like a bank or a convenience store. We don't need 480 volt service. We don't have huge motors or huge demand. So again, we'd have our service entrance rated switchboard. And if we had air conditioners, maybe they're 208 volt three phase, we can connect those directly. We could have a lighting board. Nowadays with LED lighting, we can run 120 volt lighting circuits if we're not going very far, or we can run 208 volt lighting circuits. And then since our main service is 208 volt three phase, we can have a distribution board and break that out and get 120 volts line to neutral with no transformer. So this is a simpler installation, but again, a much smaller installation. And then we have emergency power. Emergency power, then this is conventionally based on a generator, either natural gas or diesel. We'd have some transfer switches. The transfer switches would then take over and feed various distribution boards or lighting boards, depending on our installation. This is a gross oversimplification of an emergency power system. Depending on your facility, this thing can be this simple or extremely complex. Especially in healthcare, into NFPA 99, Chapter 6, talks about how this has to play and how it has to be broken up. So again, if you're in the healthcare space, by all means, get familiar with 99. National Electric Code also talks about components of an electrical emergency system as well. So let's go in a little deeper dive on some of our components. We talked about switchboards, and within our industry, there are a lot of terms that get used in a variety of things. There's switchboards, switchgear, panel boards, load centers, so on and so forth. Switchboards and switchgear sometimes are used interchangeably. Switchboards are the large items. This is where the service entrance comes in or main distribution occurs. All right. They're typically large, physically large, 3 feet wide, 4 feet deep, 7 feet tall for the biggies. And then you start lining them up as you get larger and larger. Typically, there are not a lot of connections in each switchboard because these are large connections, large current demands, current capacities. So we need a lot of physical space. Typical sizes, switchboard, you start around 400 amps and go all the way up to 4,000 amps. All right, a 4,000 amp switchboard is not going to be a single 3-foot unit. It's going to be several units bolted together and connected with a bus, typically. The switchboards are going to feed distribution or panel boards, okay? These are typically driven by geography. And we're going to talk a little bit about where these things get located. Most often, these are found in electrical rooms, and these are going to be a little bit smaller, and they'll have more connections depending on what they're doing. And the reason we want to locate these by geography is, as we know, voltage drop is a consideration, and the higher the voltage, the smaller the conductor we can get for the same distance. So we want to be very judicious as we place our panel boards, so we can maintain our costs, okay? Which is why we have transformers, all right? Transformers change the voltage to what we need. It's cheaper to run higher voltages longer distance, and the NEC has guidelines for acceptable voltage drop. And this is basically just due to the I²R losses in conductors. So if we get the voltage up higher, the current stays lower, and our conductors become less of an issue. The thing to remember is whether we're at 480 or 208 or 120, all of our conductors are rated the same. They're all 600 volt conductors. So we don't save any money by going to the lower voltage. We actually save money running at the higher voltage because the conductors are smaller. A couple other comments here that we talked about already. 483 phase is 480 volts line to line, 277 line to neutral, and the older lighting systems used to use 277. Newer lighting systems use multi-voltage drivers. That says you could go as low as 120 volts for your lighting circuits. Whether that makes sense or not would depend on the size and the distance. It's also nice to know that if you've got an existing 277 volt lighting system, you can retrofit it with new LED lights and not change any of the wires. And then 480 volt, we transform that typically to 208 three-phase, which gives us our 120 volt convenience voltages. Back to you, John.
Thanks, Jeff. I'm going to say this really slow because this is a really important point. The safest way to work on any piece of electrical equipment is to have it fully de-energized and locked out. You can't electrocute people and burn down buildings if it's turned off. Unfortunately, it isn't always possible to energize electrical equipment that's being worked on, operated, and interacted with. So the question is, if we can't turn it off, how do we quantify and mitigate that risk when we can't de-energize the equipment? We constantly talk about reliability and uptime to make sure that we have more than enough capacity to serve current and future loads. But in the same breath, if something bad happens, we have to have certain design and operation principles and practices. This is where OSHA and NFPA 70E come in. Although the NEC is not a design manual, it does contain prescriptive practices regarding how distribution systems are designed and installed. You know, things like, service clearances that Jeff will talk about later and some other constraints. However, the NEC is not intended to tell you how to operate that equipment in a safe manner after it is installed. So why is that a concern? Well, if you take a look at the little factoids on here, you can see that in the early 1970s, up to 14,000 workers were being killed on a job each year. So in 1970, the Occupational Safety and Health Act passed. This act is often referred to as the Safety Bill of Rights and led directly to the formation of OSHA. The goal of OSHA is to ensure safety and healthy working conditions for anybody, to ensure good work by setting standards and enforcing standards. So the Act says that you need to provide a workplace that is free from known and recognized hazards. But how do you do that? The part of the federal regulations associated with the occupational safety and health standards for electrical installations, if you feel like looking up, is in this outlink on this particular page. Aside from having a whole bunch of blank sections when you go through it that are reserved for future use, you'll see that a lot of the safety design standards strangely mirror that are within the NEC. You also see that the sections related to operation and maintenance of the electrical equipment is oddly vague in detailing exactly what safe work practices. And this is where NFPA 70E comes in. OSHA considers 70E as the primary consensus-based standard that addresses electrical hazards in the workplace and goes into significantly more detail than Part 1910. So while OSHA does not specifically enforce 70E is often used as the fine print to support OSHA's own standards. It's expected that those blank sections that we're talking about will eventually be rewritten to reflect the requirements of 70E, just like some of the parts already reflect the NEC in the earlier portion of 1910. Okay, so we established that there's a distinction between the NEC and 70E. The NEC is primarily design and installation, and 70E is primarily operation and maintenance. But on the operation and maintenance side, when we think about safe work practices, the best way to ensure safety when maintaining electrical equipment is to de-energize and lock it out. However, there are multiple situations where turning that off is not desirable or feasible. Data centers, hospitals, what have you. So if an electrician needs to work on that piece of equipment while it's still energized, how do you mitigate the hazards associated with that? And more importantly, how many hazards do you have? Typically, the first thing that comes to mind when you discuss hazards is arc flash. The question is, what can you incorporate it into your design to reduce that hazard? The NEC started to address arc energy reduction starting with the 2011 version. The original requirement was just limited circuit breakers in 240.87. However, this is accomplished for, however, the requirement for fuse switches that you see here, 240.67, wasn't added until the 2017 version and recently just took full effect. How we accomplish this arc energy reduction for fuses and circuit breakers is slightly different, and we'll talk about this in the next few slides. So the energy released by an arc flash is characterized by the equation I squared T, with the variables being current and time. So based on that equation, limiting the available current can have a significant impact on the amount of energy released. However, for many installations, you can't adequately serve your load unless you have that high capacity electrical distribution equipment, so you're stuck. If you can't limit your fault current because you have really big equipment, you have to address the other component of I squared T, basically the time component. You have to clear the fault as quickly as possible. If you remember in those previous slides with the time current curves, both breakers and fuses react quickly to bolted faults in the instantaneous region. Remember that dogleg curve and that dogleg and the half to one cycle range of a Mulliken circuit breaker? However, the magnitude of current associated with arc flash faults are typically only a third to half of the magnitude of a full-on bolted fault. This puts us in a different place on the time current curve. So the code requires that we provide some type of arc energy reduction. And for fuses, that's for 1200 amps and larger, same circuit breakers. If that fuse can clear an arc fault in 0.0 seconds or less, you don't have to do anything else, but that's dramatically harder than it sounds. Again, the minimum and maximum melt times for a fuse aren't adjustable like a breaker of a solid-state trip unit. In most cases, you're stuck providing some type of supplemental tripping device. The code gives you 5 options here to accomplish this, but unfortunately, implementing most of these 5 methods, you're basically duplicating functionality that is much easier to accomplish with circuit breakers. We'll see in the next slide that most of these improved methods are duplicated for circuit breakers. So with the exception of zone selective interlocking and instantaneous trip settings, you can see that the methods clearly mirrors that for fuses. I can spend a whole bunch of time on this slide, so we'll probably answer a couple of these, a couple of questions about these later on in the Q&A section. Alrighty. Oh yeah, going back to the previous slide for one quick second, there is one typo in this slide. There is one additional method, which is having an adjustable trips, an instantaneous trip setting that meets the requirement. All right, this is a big backwards. We probably should have talked about exactly what an arc flash is before diving into the code requirements. So let's make this quick. Let's focus on the last 2 bullet points in this slide. Arc flashes usually don't happen spontaneously when no one is around. Normally, they are the direct result of someone interacting with the equipment. That person is typically doing something that initiates the event. It might be racking out a breaker, it could be dropping a tool, whatever. We're running on short of time, so let's make this quick. Again, the arcing current will be significantly less than the bolted fall current, somewhere around a third to half of the bolted fall current. You're conducting that current through an ionized plasma, bridging an air gap between energized conductors and a grounded component. When it happens in an enclosure like a panel or switchboard, the enclosure serves to magnify and direct to release energy, which makes it more dangerous for an electrician working in front of a piece of equipment. Okay, Jeff, let's bring this into the home stretch.
All right, thanks, John. Let me see where we want to go. All right, so basically, arc flashes are dangerous. Wherever there is one, you want to be somewhere else. So in terms of space requirements, the code is very prescriptive, but basically bigger is better. And location is key from our perspective, but it makes the architects hate us, okay? But we want electrical rooms to make sure that they're big enough, they're safe, they're convenient for our maintenance folks, and they're located in places that it makes sense for our electrical system, so we're not running huge conductors all over the building back and forth, okay? Maintenance likes them near the equipment. Architects hate to give us the space for them, but that's just what, you know, we have to deal with in our world. NEC dictates how many things are allowed on a circuit. NEC dictates wire size based on load. All of those things are going to come into play when we design our electrical system and start to lay out our rooms. NFPA 70 rules, like we talked about, it's all about safety. Article 110, you can read the code, gives you all the details about space requirements. I'm going to fly through these. Basically, 3.5 feet is your friend. I know 3 feet is the minimum, but go with 3.5, and then you're always safe unless you're going to deal with medium voltage. One thing to be careful of here is NEC characterizes a brick, block, or tile wall as a grounded surface. So that kicks you into the 3.5 feet space, okay? Keep that in mind. Egress is also governed by NEC. Personnel doors are required, at least one, maybe two, depending on the ampacity of your switch gear. You can play games with doubling the working clearance. Greater than 800 amps, you got to have panic hardware, and the door has to swing out so we can get out. Various other rules here you got to be aware of. And also the last one here, know who your authority having jurisdiction is. I can't tell you the number of times we get into code discussions with the AHJ about how different things are interpreted. So know your AHJ, know what they like, know what they don't like, and your life will be much easier. Okay, if you go over 1,000 volts, the rules change. Basically, the clearances just go up. Okay. Future proofing. This is very important as a design professional when you're creating spaces and you're creating systems, to get with your clients and help them understand, are you ever going to grow this facility? Is this phase one of a multi-phase installation? It's much easier to leave space in the original design than to try and come back later and shoehorn something in. We had a little video there, but we're not going to show it. I don't know if it'll be available. Maybe we can make it available to you after the fact. But it shows how we tried to shoehorn some equipment into an existing electrical room, and it was quite an adventure. We were able to do so, but it did work. So real quickly, let's talk about medium voltage. You know, we talked about I squared R losses in conductors, and one way to get those down is to get the voltage even higher. So medium voltage, what is it and why would I want to use it? So here we've got an ANSI standard. Okay, ANSI standard defines medium voltage as 2,400 to 69,000 volts. Another definition specifies medium voltage as 1,000 to 35,000 volts. So the answer to the question, what's medium voltage, is it depends on who you ask. But for all intents and purposes, I think anything over 1,000 volts you're in the medium voltage range. 69,000 is kind of high. 35 is probably a better number. It just depends on what you're doing. When you're getting into that class of voltages, 35 and up, you're actually starting to get into electrical distribution as opposed to facility type work. And then industry breaks it down by classes of the end use equipment. 4160 volt motors are very common, and that's what's considered 5 kV stuff. 1247 is a common underground distribution for medium to large installations, cargo terminals, for example, that have great distances to cover and large loads. That's in the 15 kV class. You'll also find 13,000 volt distribution. I actually ran across a distribution voltage the other day when I was out for a walk that I had never seen before. It was 19,000 volts. So there's a variety of things out there. So why do you want to use it? It's common. We talked about rural overhead distribution. It's an equipment requirement is what drives it. It's driven by what are we doing? You know, a 3,000 horsepower motor, and where would you have one of those? A water treatment plant, a wastewater plant, you know, something that's moving large amounts of something, in this case, water. You know, it's 2,700 amps at 480 volts. I can't even imagine how you would run conductors to that thing, if you could even find one. But at 4160, it's 300 amps. Piece of cake. You can get 15 kV or 5 kV cables that do that all day long. The higher voltage means the conductors are smaller. The insulation is better and different, obviously, because the voltage is higher. The switchgear gets larger, usually deeper, and a lot of that has to do with the arc capability of the higher voltages. The switchgear, of course, is more expensive. There's a whole line of arc attenuating switchgear when you get into medium voltage class. And it's a different maintenance model. If you're an existing facility that's got folks that can maintain 480 volt equipment, if you throw 4160 into the mix, it's very different for them. So you got to keep that in mind. So basically, use it where it makes sense, and the ROI and the geography support it. And with that, I will give it back to our lead presenter, Amara.
All right, awesome. Well, thank you, Jeff, and thank you, John. That is a ton of information. And we're going to take some questions now. So please type your question into the Ask a Question box, and we'll get to as many questions as time allows. Questions that we do not get to will be posted at www.csemag.com with the archived version of this webcast. To download the presentation slides, please use the event resources on the left side of your screen. Don't forget, you can earn continuing education for this. So you will have to take an exam at the end, but you'll get 1 hour of continuing education. All right, Jeff and John, we are going to start with the questions. John, this first question is for you. Can you please explain arc flash reduction switches? Hey, John, I'm going to jump in here. If you could please unmute yourself and explain arc flash reduction switches. Thank you.
Thank you. So you can see in this picture here, this is a maintenance switch. Basically, this switch is interlocked with the electronic trip unit for a circuit breaker. Basically, when you enable this switch to turn the maintenance mode on, you are forcing that switch to defeat any type of time delays that it has in the instantaneous region. Again, with the I squared T equation, we're addressing the T component. We're making this breaker operate as quickly as possible to reduce that overall magnitude of current. The downside is that switch is a manual function. You turn it on and off, so you lose all your protection or reduce your protection when you're in normal operating mode and that maintenance mode is turned off.
All right, awesome. Thank you, John. Now, Jeff, the next question's for you, and you touched on this a little bit, but if you could give us some details, what's the difference between high voltage and medium voltage? Could you give us those ranges, please?
Sure. So I'll even go so far as let's talk about low voltage. And low voltage is anything up to 600 volts. So typically, most of us are going to operate in the low voltage range with our 480, 240, 208, 120. Medium voltage, depending on who you ask, is either 1,000 to 35,000 volts or 2,400 to 69,000 volts. And then high voltage is anything above that. Typically, we are going to operate at medium voltage, we're going to operate in the 4160 or the 5 kV range, or the 1247 13,000, which is the 15 kV range.
Okay, lots of numbers there. Got it. John, the next question's for you, and I'm going to combine a couple questions. So if you need me to repeat anything, please let me know. So talk about circuit breakers and zone selective interlocking. So the concern is controls, communications, bringing all these things together and selecting the right methods. Can you talk about that a little bit, please?
Sure. So with zone selective interlocking, you have multiple breakers in series, each with an electronic trip unit and all interconnected through a communication bus. So these breakers can communicate with each other, and you can basically communicate where a fault is happening in respect to any of those individual breakers. And typically you want the breaker that's closest to default to operate first. So when that breaker that's closest to default operates first, it is inhibiting the tripping of breakers that are upstream. So you can limit that interruption to your current to the smallest portion of your distribution. However, when you're inhibiting the tripping of the upstream breakers where the most amount of fault current is, that really doesn't do anything for you from an arc flash standpoint. So you're going to use the benefit of being able to sense current at each one of those locations and flip it on its head. And basically, while in the traditional selective coordination with zone selective interlocking, instead of tripping at the breaker downstream, you're tripping the breaker at the main to quickly clear that fault as possible. So basically, the breaker at the main sees current coming in, but the breaker downstream doesn't see the current going out. So you know by natural logical function that the fault is occurring at the main, and then you have an arc fault condition that you should trip that breaker quickly.
Okay, great. Thank you. We have a lot of questions here. If you do have a question for one of the presenters, please type your question into the Ask a Question box. We'll try to get to as many as possible. Jeff, for you, this next question, and I can rephrase or reread anything. This kind of goes back to your sizing portion where you talked about sizing electrical rooms. Mm-hmm. Can you talk about initially sizing these electrical rooms at the beginning of the design when you don't know the load or the demand on that particular building?
Sure. Just draw a box around the whole building and say, this is it. No, in all seriousness, yeah. You're going to have, the loads aren't going to be known, but you're going to have to make some assumptions, 5 watts a square foot, about how big the building is, go from there. But in all reality, make it twice as big as you think you need to, because then you can always negotiate with the architect when they're screaming for more space. And take more than just the code into consideration. Consider that the maintenance guys have to get in there. If this is high current switch gear, they're going to have to roll breakers in on carts. They're going to have to rack them out. They're going to have to maneuver. So be kind to the maintenance folks, and they will appreciate it.
Fantastic. Thank you. And Jeff, this last question is for you. We only have time for one more, it looks like. Again, this kind of goes back to the sizing and the design of electrical rooms. Can you talk about the panel layout and placement, and then put that into perspective with voltage drop?
Sure. So obviously, voltage drop is clearly a function of the current we're going to try and run down the wire, and it really becomes a cost discussion as much as anything else. If we're going to run a lot of current a long distance, we're going to pay for a lot of copper. We have a cost associated with that versus taking up another 100 or 200 square feet in a building. And that's a negotiation that has to happen with the architect. Ideally, our electrical room would be right smack in the center of the building, so all of our runs would be as short as possible. But we know that's not realistic. So we try and compromise. If there's an elevator core, maybe we can get near there and just go vertical in the building. So it's really just a return on investment kind of discussion based on what the building is going to be used for and how much space the architect can give us.
Got it. All right. Well, thank you. That's some terrific information and a lot of information. I'd like to wrap up by thanking these extraordinary subject matter experts, John Yoon and Jeff Thomas, for sharing their extensive knowledge of electrical rooms and design. I'd also like to extend a special thank you to our sponsors, ABB, Cyber Sciences, and Starline, a brand of Legrand, for supporting this education session. Before you go, we need your feedback to improve future education sessions. A short survey will pop up on your screen as soon as this webcast ends. Please take a few moments to complete it. Finally, on behalf of Consulting, Specifying Engineer, and CFE Media and Technology, thank you for joining us. We'll see you at the next education session. Thank you, and goodbye.